currently serves as Assistant Commissioner for the Polk Soil and Water Conservation District and serves on the Technical Committee for the Iowa Stormwater Management Manual.
Thank you. One quick update to the bio. I actually live in Dubuque, Iowa now, and I'm on the Catfish Creek Watershed Management Authority. No longer serve on the Polk County Soil and Water Conservation District as an assistant commissioner. So, we're going to jump right in here. So this is a project. It's a very focused case study on a campus that we've been working on for 10 years in La Crosse, Wisconsin. It's about 3 hours and 45 minutes north of here. We're here in Ames. You head up to Albert Lee and take Interstate 90 over to La Crosse, which is in the Driftless region. Our project location is located about 6 blocks from the Mississippi River. And so here is the campus. If you're familiar with La Crosse at all, you come in from the west into downtown, and you can see by the amount of impervious cover here, it's a very urbanized environment. And so we are working through a number of considerations really early on as it relates to stormwater, and this college really took this seriously. And so you can see their proximity here. The blue outline is their campus boundary. The Mississippi River is right back here in the background. There's actually a bog on the north end, and they're located on a historic floodplain along the Mississippi River. Our project started in about 2008. In 2009, we completed a campus master plan. One of the key things coming out of that was they wanted to identify as a 21st century campus. And what does a 21st century campus look like? And so there's a lot of emphasis on really trying to be cutting edge at that time. This is 10 years ago when we started thinking about these things. And so multimodal transportation was a key thing. They wanted to connect to the community. University of Wisconsin-La Crosse was there. Viterbo was also there. And so there was a culture about using transportation that wasn't always reliant on your car. They also thought very heavily of rainwater harvesting, green roofs, cisterns, permeable paving, best management practices, stormwater infiltration. So these were all key things to them that would define who they were to the community and to the state. So we took a watershed approach, and keep in mind we've been thinking about this for about 10 years, and so we're going to go through a lot of information here. But one of the key things as part of that master plan was to integrate best management practices on all the projects. That was just a given. You will do this. And so that was really a great thing to be a part of. Some of the other key things is that they wanted a reduction in flow for the 10-year event to help them comply with the City of La Crosse's stormwater utility. In La Crosse, the utility is $13 per ERU, and so that's significantly higher than most of the credits or the rate structure within the state of Iowa, and so there's actually a financial payback to doing some of these things. We were also helping them renovate from a sustainable design standpoint quite a few buildings on campus, and so we were serving as the lead consultant, our architecture branch of RDG, and helping them identify strategies. And so as part of that process, we wanted to make sure that we complied with all the lead credits. And so there are a number of layers here that we were working towards. One of the key things, they had set up this east-west axis through campus, and then what we'll dig into here in terms of what we're calling our 8th Street project is this corridor here, which was really also wanted to complement the primary flow of pedestrian traffic, which was on an east-west basis, but they also wanted to, as they grow, residential uses were up here, and then to the east, which is off the screen. They wanted to bring these people safely down into the heart of campus, which is really these 4 buildings. When we're thinking about a watershed approach in an urban environment, we also have to be mindful of where the water is going, where it's coming from, what the existing storm sewer capacity was. We had a 60-inch storm sewer that was 100 years old, built out of brick, 18 feet below grade. And so that was surcharged 6 blocks away from the Mississippi River, and so we had to be very careful about adding more water to that. We knew that we were trying to remove water from that system and get it into the ground. We had good sandy soils here, so we were fortunate they were able to do that. But every space that was on campus, we had to think of if it was green, because about 90% of the campus is impervious. Any green space we had, we wanted to also think about it as blue space. And so we had this parallel track that if it was an open space, it needed to also function. So we were trying to work through all of those layers as part of that master planning effort. We had a number of systems that we identified through that project. Stormwater planters, which is one we'll focus on, but we also, all of the plantings had soil health was a component of that. We used permeable pavers where it was possible, rain gardens, bioswales, and porous asphalt. And so all of these practices are on the campus and have taken shape over the years. We also helped with a green roof and then a 15,000-gallon rainwater cistern that we've actually been able to capture water and use that to irrigate all of the plantings for 7 city blocks. So it's a pretty comprehensive, there's a lot of layers here, and when you're working in a city that's 100 years old, there's a lot of infrastructure below grade that you don't see. In 2009, we did the first project that was built, and we did these, there's a courtyard project, but the thing I want to focus on here is these traffic calming bump outs. And these were designed to, this is that east-west axis, this is one of the courtyards that was on the west end of it. We put these bump outs in here to slow traffic, but then also use them as an opportunity to infiltrate stormwater. And we had to rely really heavily upon the Portland Stormwater Management Manual to get us going in the right direction. This was, you know, kind of cutting edge at that point in time. And so we didn't know a whole lot about it, but we did a lot of education, or educated ourselves and did a lot of research, reached out to folks in Portland to talk about it. We came up with this master plan, and then ultimately these bump outs right here had, we called them stormwater planners at the time. Fast forward to construction, and this was really a nightmare. You know, our survey wasn't the greatest, and sometimes things get missed, but when they opened up the street, they found a 6-foot by 6-foot duct bank with the city of La Crosse's primary. And so we had designed this great system of all of these sediment sumps that water would flow into the back of curb, the sediment would drop out, and then it would overflow into the planter and then infiltrate. That no longer could happen, so we had to rethink how that system happened. We ended up putting basically erosion control stone on the surface and then having them, they come back and replace that every so often. We were able to get it in these 2 planters here, but then in the back here, which is where that bump out is we had to go to all surface treatment to remove the sediment. And so we did it on both sides of that city block of this courtyard, and it took an entire summer to do 6 planters, all cast in place, down to frost so they wouldn't move. There was limestone monuments and gateways on top of them. And it really just took a really long time. And after talking with the college, we thought, you know, we need to find a better way. And so fast forward to 2000, well, I guess a couple years later, we started thinking about this project, and it didn't get built until 2016 and 2017. We call it the 8th Street project, so this is the north-south pedestrian axes. It's also a fully functioning street. The project we were talking about just a moment ago was right down here on the east-west axes for students. This is an image of what it looks like before, not very conducive to a friendly pedestrian environment. A lot of parking lot right up to the street, not a lot of open space, not a lot of buffering, not a lot of vegetation. Pretty harsh environment, and this is looking south down that street. 2010, the college said, we want more green space, we have none, and so they asked us to look at a number of site plans for these parking lots. The photographs we just showed you were taken about right here, one looking this way and one looking this way to the south. And so we wanted to find a way that we could save parking, because that was in demand, but then also add more green space and really create this pedestrian mall that students could traverse up and down. We met with the city, and that was really a no-go. From a city planning standpoint, if you put your planning hat on, you don't want to interrupt the grid. So we were kind of trying to balance the campus planning versus city planning ideas. And so we came up with this idea of, let's request a street vacation, but only for half of the street. And so in 2013, we presented the idea of a complete street concept where we would actually vacate 30 feet of right-of-way on each side so we could put in the pedestrian improvements we wanted and also use that area to infiltrate stormwater. Most of the time, if you're familiar with the regulations of any community that has a stormwater utility, you can't use public space to infiltrate stormwater. And so this was our way of getting around that. We basically built a public street, but only half of it was really a city street. The city then got an easement back over the portion that they vacated, so nobody really knows the difference, except for now we can take credit for infiltration within that area. As part of that agreement, we also agreed to manage all of the city stormwater through one system, so that there wasn't city water, private water, it was all together. And so finally in 2014, the city approved the partial street vacation, and then we moved forward with construction drawings in 2000, the preliminary and final design phases in 2015 and 16. These are some of the key things that we had to go through as part of that process, was looking at pedestrian-centric street. The city had just passed an ordinance that promotes complete streets, and they also needed to be green, so bicycles moving through here, pedestrians moving through here. We didn't actually have a bus system on this street, but they also wanted it to be safe for people, have appropriate lighting, places to sit. And then there's also the very pragmatic things of where are we going to put the snow? And so we had to go through an analysis of actually having we actually ended up with more snow storage area because we had less street to plow. We had to talk, and so we had to think about parking, and what are we going to do with all the parking that's on the street, because we actually were removing on-street parking. And so as part of the long-term campus planning, we looked at adding stalls elsewhere within a parking ramp. The college valued open space more than it did parking, so we had to work through that. Public sidewalks, showing them how the new sidewalks would be virtually in the same location, but would be better served because they would look better, they would be wider, they'd be more accommodating to the larger flows of pedestrian traffic. Utilities, again, with it being a very old community, there was a lot of utilities, and we found quite a few underneath the street when we opened it up.
They were always right where we thought they were going to be, right?
Exactly, yeah. A new fiber line that wasn't on the survey, that was fun. Street trees, trying to make sure that we preserve the healthy ones that are there, and there weren't a lot. And then also adding in, this is a Tree Campus USA, and so they really valued having that canopy. And so finally we kind of came to this, after the city and the community came together, these were the kind of the key things that were the benefits: reducing the stress on storm sewers, the city was going to get a new street, reduction in plowing, new infrastructure, it's going to be a complete street, and reduction in maintenance. So now we'll jump into, Greg will walk us through the engineering, and then I'll jump back into some of the design of the components.
Thanks, Ryan. So what we're showing today is really one of about 3 pieces that I've been directly involved with. I kind of joined this project mid-run. I joined RDG late in 2014, so I've been with this project for about 3.5 years now. So this is just one example of how we looked at stormwater. We really wanted to make it hard for water to move off the site. We weren't looking at, okay, we're going to have a practice on a site. We were looking at dividing the site up into multiple areas of drainage and really trying to look at installing practices in sub-watersheds scattered throughout the site. So you can see kind of a drainage map and zooming in how it all looks. Water that's draining into some of these central islands, and then also some of these planter boxes through inlets, which we'll show some pictures of in a little bit. So we really had to look at this on a technical level. We had to break it up into watersheds. We had to analyze, okay, what's the impervious cover in each of these watersheds? Really get an idea of, okay, open space, impervious cover, what are our runoff curve numbers, what are our curve numbers for both water quality and for the larger storms. So breaking it down in a lot of detail for a lot of small sub-watersheds. We then incorporated this into 2 different types of stormwater models. One, many of you may be familiar with the TR55 model, so you're actually developing a hydrograph where we're looking at these different areas, the areas they shed, the percent impervious, and how quickly it moves off the site, and having the computer program run a simulation and figure out in a single storm event, what is our peak flow going to be? So one event at a time. And our big concern there was we were trying to reduce flow for the 2, the 10, and the 100-year storm events because that was one of the city requirements. And another analysis that we did is in the state of Wisconsin, when you do infiltration practices, you have to do a wind slant analysis. So this is a software program that's been developed And it's actually fairly easy to use, but you can analyze these practices actually, and you run, instead of a single event simulation, you're running a 30-year simulation. So it runs multiple storm events based on, for this area, they took, I think, rainfall events that happened from the 1960s to the 90s. So they're actual real rainfall events that happen that they feel like this 30-year period is representative of what would normally happen in La Crosse. So you take that, you enter in all your information about your different stormwater practices. This happens to be for a bioretention area, but there are other practices in the software where you can enter the properties and how you've designed it, and then you run it through the system and it'll tell you how much flow you've reduced, how much of different pollutant loads that you've reduced. So you're not just looking at a single event peak flow, you're looking at overall volume reduction and overall reduction in pollutant loading. So you can see on the screen here where it spits out and says, okay, this is how much the yield, how much less you're going to have in particulate solids, total solids, and phosphorus. Those are some of the things we were looking at on this project. So we looked at all of these sub-watersheds and practices and then had to comprehensively, for all these sites, this is just an example of one of the sites, but for all these sites, get to an understanding of how we were doing on a site-wide basis. So you can see here on the column on the left, that's the total input loading and TSS that we have, and then the output, and you can see the reduction from all these improvements collectively. We're expecting almost a 90% reduction in TSS from the site. And Wisconsin requires, on sites like this, a reduction of 80%. So we actually exceeded the state requirements. On the other side of it, as I mentioned before, we were also looking at peak flow reductions. One of the keys, not only to meet the city standards, they were looking for reductions for all these events, but in order to get the credits for the Stormwater Utility Fee credits, that's tied to reduction in the 10-year event. And you can get up to a 50% credit for that. So in this analysis, we were able to reduce that peak runoff during that storm event by about 23%. And then you can take up to a 50% credit for your TSS reduction, and obviously we exceeded that. So our total ERU credit is 73%. So what that means is, at this site, Ryan mentioned that their fee is $13 for every equivalent residential unit in their city. I don't remember exactly how many square feet that is, but I think it's around 2,500 square feet for an ERU. They're paying $13 for every site, for every one of those that they have. Well, after these improvements, they're able to work with the city and reduce that fee by 73%. So, they're only paying $2 or $3 a month instead of $13 a month for their site. So there's a big financial impact for them. We can also dig deeper into the numbers on this, and you can get not just our volume reduction that we talked about, the TSS reduction, but phosphorus reductions. And again, we're seeing similar reductions in that, almost 90% on our phosphorus reductions. And a lot of this is tied directly to the volume reductions we're seeing at this campus. Very significant volume reductions. You can see on this one site, this is one of 3 sites, but at this one site, over 650,000 gallons every year is reduced from the site. And this is only about a 2-acre site. So very significant reductions in flow that are going into the storm sewer system and going into the Mississippi River. And with that, we're also reducing suspended solids, and we're also reducing phosphorus loading. So when you sum this up, we've done a comprehensive analysis of not just this project, but the 2 previous projects that have happened over the last 3 years that I've been a part of. And if you combine all of those projects together, remember, this is on a very urban campus. These are parking lot renovations. They're very, very impervious by nature. But we're seeing, as opposed to if you compared it with if we did nothing, if we just did curb and gutter, storm sewer, and let it all go, we're seeing an overall volume reduction of 80% on an annual basis. So an 80% volume reduction, that translates into about 1.7 million gallons of water every year. And if you translate that to this specific site area, that's equivalent to about 9.4 inches of rainfall. So every year, 9.4 inches of rainfall that used to fall on this site and go to the Mississippi River is now staying on site and being used by plants, or it's infiltrating into the ground. And one other aspect of this that's really interesting is just all the layers of permitting that we had to go through for this. You had La Crosse has its own review and construction applications. There's also they call their program, instead of NPDS like we call it here in Iowa, it's WPDS, but it's basically the same thing. You're doing an erosion, sediment, and pollution prevention plan, and you actually have to do you have to send in an Excel spreadsheet that they designed that shows that you have to meet certain loadings. You have to be below a certain tons per acre per year, and you have to show that you're putting practices to reduce that by a set amount in order to get approval of your SWIP, and you have to send that into the state for approval. Also, I'm highlighting here, there's also a state plumbing permit, so if you have any kind of infiltration practice, you have to go through this permit with the state, and because there's only a certain number of people that work at the state, you need to keep that in mind, because on our first project, we all kind of got into a panic because we realized we kind of had to do this. We didn't realize that there was a 2-month waiting period to get the review done. So we begged and pleaded, and they were able to expedite it. Yeah, you can get an expedited review, but you have to double the fee to get it reviewed quicker. So we were like, okay, well, we'll pay the extra fee, we'll get this on. So when we did the next phase of the project, we're like, okay, we're not going to do that again. We're going to pay attention. You go online, you get a scheduled time, and you send your plans and your calculations, and you have to do an operation and maintenance plan, and you send it all into the state electronically. They review it, send in some comments to you, and make any revisions. It came back pretty clean. Made a couple last revisions, and then we had approval. So really, once we got in line, it didn't take very long. It took maybe like a week or two, but it was just getting in line that was the trick. So, and then of course the stormwater credit application that we talked about, when it's all done, then we had to show evidence that we already had in our stormwater report that, okay, we've reduced flow by this amount, we've reduced TSS by this amount, we're eligible for these credits, so that ultimately our client can be saving money every month. And a couple things that went with that stormwater permit were this soil evaluation form that a geotechnical engineer had to sign that proved what we thought the infiltration rates were going to be for this practice. And then you can see their handy-dandy checklist, review checklist. This is one of 2 pages where you have to fill it out and identify exactly how you're fulfilling their requirements. So I'm going to toss it back to Ryan because he's got a lot of great pictures to show you. And I've showed you enough numbers already. Here you go, Ryan.
Thanks, Greg. So one of the things that we always try to do on our projects is make sure that we're using stormwater as an amenity, something that is not just sent downstream in a pipe. And so we thought very hard about how we can take the water from both the private side, which was in this circumstance here, the parking lot, and then the water from the street, and use it to beautify the campus. These were various sections that we did early on to kind of show how these systems could work and then how water would move down the street and get into these stormwater planters. In this particular scheme, here's an exploded axon. Water would flow down the gutter, it would spill over into a sump, and then once the sediment drops out, it would fill in into this stormwater planter. The final design ended up changing. Here we were exploring the use of a runnel to help spread out the water. We ended up eliminating that as part of the project. We also wanted to make sure we had trees, and so we had a lot of care put into the design to allow tree roots to go out of these knockouts. And then one of the things we did on top of it, because we were, again, trying to get water across the public right-of-way and then from the street, we put bar grading over the top so that people could see where the water is coming from and where it's going. And it would also be a part of the design and something that would help subtly communicate that there's more going on in this street than you might think. And that was a very important part of Western's academic mission, was leading by example and demonstrating. And so they were all about showing off the system. And these are various models. And going back to my earlier comment about that other project taking forever, we developed this system, consider it Legos, that could be put together in these blocks, these precast walls, and you could assemble them in a 9-foot planter, a 12-foot planter, an 18-foot planter, or a 24-foot planter, or 36. And so it was scalable so that when Greg was doing the stormwater calculations, we could use our kit of parts, precast parts that were going to be picked off the truck and set in place, and have it go very quickly. Rather than taking months, they were able to get all the planters in a week and a half. And so it significantly expedited the time that this project took place.
And just to highlight that, so on the side pieces, you only had 3 different sizes, right?
Yep.
So they could be cast off-site in one location in 3 different sizes, and then assembled on-site to make the different sizes of planters. And then we had the end cap. So there wasn't a lot of customization. It made them a lot more, not only quicker to build, but more cost-effective to manufacture.
A few photographs of construction, which I'm sure our insurance company wouldn't want you to see. But these are the footings going in, and you can see they've embedded the plates here where you would weld the corners. We did a mock-up, and this isn't, these planters weren't, colored concrete. We were trying to keep them very raw, but then put a really nice, a nice finish on them. It was kind of a borderline between an architectural finish and then a precast, just storm sewer, kind of finish that you get from that. Here they are going in. Some of the planters did have a stormwater function, and then you can see here some of them didn't. And so those that did not have a stormwater function didn't have to be nearly as deep. One of the things that you're not seeing in here is that, I'd mentioned we found a fiber line that had just put in. We did the survey in the fall, or one year, and then they put the fiber line in the next year, and we didn't know that. And so we had to do knockouts. So we revised the design so that in the end caps of all of these planters here, we had a dog house that could be set over any utilities so that you could run them right to the bottom of the planter. So there was a lot of thought that went into how we can get these in efficiently and how they can do their job. Forming up for the frame that you can set the bar grading on.
Hey, Ryan, can you take a step back too? One thing to highlight on this is the grading that Ryan was talking about earlier. And this is how water enters the system. So on the street side, and actually on both of the sides, what we decided was it was simpler. We just took a regular intake and we built it like a sump. So there's just a regular standard precast inlet there. The water drops into it. It acts like a forebay. The water sits in there, the sediment pops out, and then as it fills up, there's a knockout in the back. Once it fills up to a certain level, then it spills through the runnel into what Ryan's going to show you.
There's a lot of in-the-field review to make sure that things were set at the proper elevations. This street had less than a 1 foot of fall over 300 feet, so it was very, very flat. You can see here we had some erosion control stone that was at the knockout where the stormwater came through. And if you remember, this is kind of the before picture, and then this is the after picture. And it rained the day that we sent our photographer up there. That's usually what happens. But you can see here all of the planters and then how they operate. And so for each one of these inlets, there's either a pair of stormwater planters, straddling it, or in some cases, like right here, only one stormwater planter and then a traditional planter next to it. Some more images, and this is just right after it was installed. And so if I fast forward, again, here's what Greg was talking about. Water falls in the inlet, there's a sump below, it spills over and it comes into here. The drop from this pedestrian surface to the top of the planter was 28 inches. We did this in 2 phases. After we did the first one, the college knew what they were getting into, this being a pedestrian corridor and people potentially falling in there. So we actually went and designed a railing system for the next phase. We received the bids on that railing system or the guard system, and then shared that with the college. They talked to their risk management insurance provider and actually elected not to do them because if stormwater management in these types of projects are going to become more prevalent, I think the thought is that we're not, it's an extra cost and it's still within code compliance. Where do you draw the line? In other places in La Crosse, we're starting to do this as well. And so...
And it looks more dramatic right now because there's no plant material.
Right, exactly. I'm going to jump ahead. These are just, the sidewalk was all permeable pavers, all native plants. And this is a year later using my iPhone, so it's not as pretty as the other ones. But you can see all of the plants we use along the buffering to hide the cars. These were, number one, containers, and then within the stormwater planters themselves, we used grow plugs, which do really well and grow really quickly. And so you can see what it looks like after 1 year of going through the winter. And then, one of the nice things about some of the natives we get to use is they are quite beautiful. So this is cardinal flower that was in bloom the day I happened to be there. So, Greg already mentioned some of the results about the stormwater utility fee having nearly an 80% reduction in their stormwater utility costs. We did a quick analysis when we were thinking about the entire campus and what the return would be, and we came to about a $62,000 return over a 25-year life expectancy. And so it does not cover the cost of doing this. So it's not going to be a wash, But when you factor in what their mission was, what their vision was, it didn't make it very difficult to do. It really helped build the case because I think they were actually going to do it no matter what. So some of the things that we learned through this process is that certainly working with your municipality and having a municipality that is all about thinking holistically and allowing us to work within their municipal infrastructure and balancing the private and the public sector infrastructure needs to infiltrate stormwater in a way that didn't happen. They actually modeled their Green Street ordinance after our first project in 2009 because it was right outside City Hall, and so they were able to kind of monitor it. And I think it's been good working with them and being able to try and do, fix, and learn and get better. And so overall, I think working together really has been a key part of making this successful. So with that, thank you very much, and we'd be happy to answer any questions. Yes?
So was TSS the only driving determination of what was done with stormwater, the way I understand it? Or what was constructive practices?
It wasn't really the driver as far as what was selected, but it was one of the criteria that the state wanted us to analyze. We had to have an 80% reduction in that. Also, that was a city criteria. And then phosphorus was another criteria because of the local conditions of the watershed they were concerned about. So we
But
did
other than
that
that, it
as
was just
well.
as much of the tenure you can produce.
Yeah, yeah. Mhm. Yeah, they don't have quite the same setup that we do here in Iowa where we've got unified sizing criteria. They do more of this analysis to see what happens with the small storms.
Pat?
I guess that's related to my question. So the process in MS4 City, do they have a post-construction ordinance that differs from the state's requirements?
It's similar, but yeah, each city has its own requirement.
Do you know what their requirement is? Does it go above?
I think as far as the TSS removal and things like that, that's similar to state requirements. They don't have anything in excess. The reduction of the 2 and 10 in a 100-year or having no increase is one of their local requirements. It's in excess of state law.
It sounds like we learned a lot from phase 1 to phase 2. Are you done, or are there more phases, or is the campus looking at other one thing?
We have touched about 65 to 70% of the campus, and they had gone through a major referendum while some of this was happening. And so there isn't dollars right now allocated for the third portion of the street. We hope that in a few years we can. Right now, we're pretty much done working after 10 years with the campus. So, yes.
I have one more question.
Yeah.
Sorry, I could ask it before, but I forgot. So the phosphorus removal that you showed, that was using wind slam and model that you get up to close to 90% fee removal? That seems really, really, really high when compared to looking at some of the research results for some of these practices.
Yeah, and I think part of that is because I don't think that the concentration in the water was reduced like by 90%, but it's because we were reducing water volume by 80%. Since we were reducing the water volume by 80% and then we have less P in the water, if we're at the 20 or 30% less phosphorus reduction in the water, yeah, that sounded really good when I said that. I'm an engineer, I got to say something embarrassing at least once during the presentation, right? So if you've got 80% less water and then you have less concentration of phosphorus in that water, that's where we're getting the 90% reduction. So no, it's not a 90% in concentration, it's a 90% in overall load. Very good question. Wayne?
Did they do any adjustment because of the tax working on the rainfall amounts?
I am not sure of that because I don't know that their state has like a published guide of what you're to use. We just use the Atlas 14 data. We just, they didn't have that chapter basically in their book. They have guidelines on how you're supposed to model things. We just use the most recent data, which is Atlas 14.
Were the planters and the permeable sidewalks hydrologically connected?
The planters, I would say that they were independent systems. So there was, in some cases, there probably was the subbase under those pavers was next to the planters. So there may be some exchange between the two, but no, there wasn't like, we didn't specifically install like poles or anything to allow that water.
There was no subdrain underneath the pavers.
And part of that was the site, we're sitting on sand at the site, so we did have a subdrain that ran longitudinally down the street through all the planters, but we didn't have any that was underneath the paver systems. And we didn't show a lot of pictures of this, but this is also part of, as I mentioned, other phases. The previous year's courtyard project was really awesome. It's got some of them are traditional pavers, but then some are porous, and they're like in bands, color bands. And there's a couple of large bioretention features with a bridge, and then another parking lot with a solar array, and there was a rainwater harvesting system part of those two original projects as well.
Yeah, it was really kind of difficult to get the irrigation system spread out. It was a spider web over 7 city blocks using the reclaimed water. And in years past, they had done a system that, you wouldn't be in favor of, a pump and dump for their cooling. And so they had all this well water that was coming into this tank at 90 gallons per minute, 90 degrees. And then we would set up the irrigation system to run at night that basically would empty the tank, because you're usually only irrigating when you're cooling. And so it was a benefit, it wasn't all rainwater. Rainwater does go to the cistern as well, and it went through a UV filter and removed all the particulates, but the primary source of that water in the cistern was actually reclaimed well water. But it could have been going downstream at 90 gallons per minute rather than being reused, so it was a good thing for us.
And they use some of that water too for internal, like toilet flushing and other
Yes.
non-public uses.
Right, do you have a sense for the design, the sizing that you use, the design criteria that you use based on the TSS removal and volume reduction, and how that compares to the same sizing using the unified sizing criteria in Iowa?
Yeah, that's a good question. So the question is, how would this compare size-wise if we use say the Iowa Stormwater Management Manual? My sense is our practices here would actually be a little bit bigger. I did use kind of our standard as a preliminary footprint, so they would comply as far as water quality volume with our standards. But you'll see that the removal rates were above what they required, and so I think I could have made them smaller, a little smaller, and still met their requirements. So my sense is as far as sizing the footprint area of bioretention systems anyway, they might be a little bit bigger in Iowa with our standards. I don't know that that's the same for every single practice, but I'd say I think pavers are probably would end up being about the same. But of course that's kind of flex still. Yeah. So I think in Iowa our footprint might be just a little bit bigger than what theirs would require.
Okay, well, thank you very much.